Good morning, friends. Navkat this side. So today I'm going to solve the GFG POTD problem, and it is sum of bit differences. And this is another problem on bit masking. And this is a very good observation problem, and you will learn very few things. And those fundamentals are going to be used in many of the problems in future also. So the question says, like we are given an array, and we need to find the pair differences, or we can say bit differences among those array elements. So like if I sum down the problem. So let's say if I have given the array as 1, 2, 3, 4, and I need to find the bit differences between them. So if I have one, bit difference would be like the definition for bit difference would be number of positions where the bits are different in both the elements, or let's say or numbers. So for one, the binary representation is 1, and for 2 is 0, 1, 0. So the bit difference is defined as the count of different bits at the same positions. So if I'm at 0 position, let's say this I'm saying as position. If I'm at 0 position, you will clearly see there is difference in bits at both the positions. This will count bit count as well. Here also there are difference in bit count. So we have another pair. Here both bits are same, so we don't have any different bits. So if I again sum down it, it is the number of indices where the bit positions are different. So if I say again for 0, 1 and 0, 1, 0, at this positions there are bits different. Here also the bits are different. 0, 0, here the bits are same. So it will not count as a pair. So 0, 1 would be one pair. So overall, we have two pair for 1 and 2. But since if I take it has say xy and yx would be considered as two different pairs. That means if it is if for us it is 0 and this is 1. So if I say 0, 1 is one pair, so 1, 0 is also a different pair. Like we will consider it as different. And for 0, 1 we have already calculated that for 0, 1 the bit difference is 2 because we have different bits. We have different bits. So for 1, 0 also, it would be like we will just do the same thing and we will get 4. Like let's say you have calculated for x pairs, and like you have calculated for xy pairs, and you know that yx pair are also like different pairs. So the answer for xy pairs and yx pairs would be same. So the overall answer would be the answer of xy pairs into 2, because either we calculate for xy and for yx, they are equally same. But since according to definition, they are considered as different, so we will just multiply it by 2. So let me explain the example given in the problem, the 2, 7 that they have explained. So for 2, the binary configuration would be 0, 1, 0, and for 7, it would be 1, 1, 1. So you can clearly see bits at this position is different, and bit as this position is different, and this is same. So here also we got 2 as bit difference. And since again this is 2 and 7, 2, 7 will be considered as one pair, and 7, 2 will consider as a different pair. So the answer we get for these xy pair, the same would be for yx. So we just multiply by 4. There will be two more pairs that would be taking 2 and 2 together and taking 7 and 7 together. But if we take 2 and 2 together, it will be 0, 1, 0 and 0, 1, 0. None of the position have different bits. And for 7, 7 also, 1, 1, 1, 1, 1, 1. None of the position has different bits. So it will add 0 bit difference to our answer. I hope the expression is clear. For 135, that would be a little bit long, but like let's say 1 and 3, and also 5. For 1, it would be 0, 0, 1. For 3, it would be 0, 1, 1, and for 5 is 1, 1, 1. So you can clearly see 1, 1, 1, so there would be no bit difference. Here is 0 and here is 1. here it is 0 and here it is 1. So this 0, like this bit difference, have a different pair with this also and with this also. So it will add two bit differences. Here also, if you take consider this one a pair with 0, a different 0, and this one having a pair with this. So these two pairs, taking these two along and these two along, have different bit at positions. So here also we get 2. 2 plus 2 is 4. This is the answer for xy. But if I consider yx also, then it would be 2 into 4, and it is actually 8. So I think now the thing is clear. This 0 will pair up. For this 0, there are two ones, or like two elements which have different bits at that same index. And for this one, we have two elements which have different bits at that ith position. We can also say that for this 0, we have one element which has different bits. So the brute force would be simply like that we can iterate for each and every pair. Like I will just write a simple code. Like you will iterate, like let's say you will iterate for I is equal to 0 to n plus I, and you will also do an iteration for n. Why I take 0? Because 1 1 is also a one pair, and you can just calculate bits at each position. Or like if you do not calculate, either you can do a XOR also, like you can say AIR XOR AR of j y XOR, because when we do XOR of two numbers, XOR gives for same bits if it gives 0, and for different bits it gives 1. So in this example also, let's say 3 and 5, if I take XOR for 0, 3 and 5, 1 0 1, so it would be 1 and 1. So where there would be a configuration that we have different bits, so there would be 1. And now through XOR I will get 1 1 0, and using like, and I can easily count these bits too by just iterating till my number, like as we count for the binary representation of a number. So since I have XOR, I can just do while my result is greater than 0, and you can say diff plus is equals to res model of 2, because we are considered about 1. And I hope you have done this code um, when you were in your initial semester, in your first or second semester. So this is how we count the number of set bits, and through XOR, since we know for different bits positions, it will give us 1. So the XOR would be in a way that it has 1 at positions where there are different bits. So through we can take each and every pair, and then by using this bit count algorithm, we can easily calculate that what are the number of bits. And since now we have diff plus is equals to, and at the end we also have to do diff plus. I think we don't need to do diff plus 2 because ij, it will take ji also. Okay, yes, I think we don't have to do this, and we can just return diff, and it would be long re is equal to 0. And if I compile, I think this would be working fine. Should be diff. Okay, but I am doing diff plus is equals to res. Yes, diff plus is equals to, okay, the variable was diff there. So that for this case, I am getting right answer. So this would be the brute force. So I hope this is clear with you, for you. Now we come up to the optimization. And for optimization, one thing you should be knowing, the Cartesian product. And I will like tell you it. So like I am taking this example only, 135. Let's say the binary representation of 1 is 0 0 0 0 1, and the binary representation of 3 is 0 1 1, and for 5 it is 1 0 1. Now, if I somehow count bits at all these positions, so the 1 bits are 3 here, the number of 1 bits is 1 here, and the number of 1 bits is 1 here. This is a number of set, we can say this is a number of set bits. Similarly, the number of unset bits I can get using the formula n minus set bit. What is it? If I can get the number of bits are 3, I know I have 3 elements. The number of unset bit will be 3 minus set bits. That would be 0 for this case. Again, 3 minus 1, 2 for this case, and 3 minus 1, 2 for this case. So now I have the number of set bits and the number of unset bits. And how this would be helpful for us, we need to count the number of pairs. We need to count the number of pairs where we have different bits at that current position. Here, all are 1, so we know there would be no confusion where we have different bits because all are 1. So we don't have any pair where it would be a conflict that the bits are different at the current position. But in this case, we have 0 here and 1, 0 here and 1. Clearly, you know this 0 and 1, that means this is R, this is 1, this is 3 and 5. R1 and 3 would be a pair. Like for 1 and 3, this would be a 1 bit difference for this. And for 3 and 5, also we have a bit difference. Let me erase these. You can easily like observe from here. For 1, 3, for 1, 3, we have a bit difference because we have different bits at these positions. And for 3 and 5 also, we have different bits at these positions. This is. And for here, you can also say this is 1 bit count. So from here, we got 1 and 1. Till now, we have got 1, 1. And now, for this one, we have, for this one, we have again this bit difference for this position, 1, 5. And for this 3, we have again a bit difference at this position. Again, we will get 1, 1. And overall, we will get 4 here. And since x, y, and yx, we have take different pairs, so we will get 8. I think I should explain this again. What I'm saying, 0, 0, 1 and 0, 1. Here we clearly can see there is a conflict for this bit, and that means there is going to be a bit difference 1. And when I include 5, this 0 will also make a pair with this, where it will accumulate a 1 bit difference again, like for this 0 and this 1. Similarly, for this 0 and this 1, we will again have a pair. And again, for this 0 and this 1, we will again have a pair. 4. So what I want to say, if I can somehow calculate 1, 0, 1, 1, and 1, 1, 1, if I somehow can calculate the number of set bits here, the number of unset bits I will be get using n minus s, the number of set bits, number of unset bits, number of set bits, and number of unset bits. Now, let's recall the Cartesian product. What would be the Cartesian product? If we have x, if we have x entities at one side and we have y entities, the number of pairs we can form using these entities is x cross y. Like if you have 1, 2, 3 here and you have 4, 5, 6 here, this one can pair up with these 3. This 2 can again pair up with these 3, and this 3 can again pair up with these 3. That means the total number of Cartesian product and the number of pairs we can form is x cross y, isn't it? Now, how we can use this observation here? I know for this particular index, the number of set bits I have is this, and the number of unset bit is n minus s. Now assume here the number of set bits. Now, uh, now say the left hand side of this Cartesian product, I have the number of set bits. Here I have the number of set bits and here I have the number of unset bits. For this case, the number of set bits is 3 and for the unset bit is 0. So how many bit difference I can get from here, or how many unique pairs I can get from it? Comprisingly, we can get 0 because there is no 0 to form pair with. And since we are looking for a 1-0 pair or a 0-1 pair, I think this is clear. Let's move to the next index. I will remove this also and I will remove this also. This also. Here we have two set bits and one unset bit. I have two set bit and I have one unset bit. What does that mean? This 0 is going to form pair with these 1 and these 1 are different and we easily get two pairs. If you are not able to visualize this, let me draw this here. If you have 1 set bits here and you have an unset bit in this there, this 1 can form pair with this, we get 1-0, and this 1 can again form pair with 1-0. Similarly, this is for xy pair. For yx pair, this 0 can again form pair with 1 and this 0 is again form pair with 1. This is nothing but the Cartesian product, the number of possible pairs we can have. So this is for this. Now come to, I know the video would be a bit long, but I want to explain you how you can observe things. For this, the number of set bits is 1 and the number of unset bits is 2. How many unique pairs we can form? We can form two pairs. How? This one, here this time we have 0, 0 and we have 1 here. This one can again form pairs with these two and this one can form pair with these two. And if I take yx pair, this 0 can form pair with this one and this 0 can also form with this one. 1, 0, 1, 0. These are this pair and 0, 1, 0, 1 if I look for yx pair. So I think now you can get this observation that if I know the number of set bits and the number of unset bits for a particular position, for this position, I can easily calculate the number of bit difference I can get from that position. Like if you know for this position the number of set bit and unset bit, you can easily know the number of bit difference I can get entirely from this index. And why I'm saying this index, now there is one more particular observation that a binary number can be represented into 32 bits. And this we all learning from first semester that a number can be represented in 32 bits. That means if I have, and what we are doing till now, we have 2, 0, 1, 0 is the binary representation. But again, we know there are zeros, but we won't consider them because they don't provide any value to us. So similarly, every number can represent it as a 32. For 5, if I have 101, so again we know we have zeros. So if I can calculate the number of set bits at each position, 135, 001, 011, 111. Sorry, 101. So I need these three. I need these like one. I need this one. So this we can easily do by maintaining a bit array. And now I will like just want to show you a code because I have like explained everything. Sorry. So this. So what I did here, I first maintain a bit array of 32 because I want to calculate bits for each position. And since we know our binary number cannot exceed 32 bits, so I have maintained 32 bits. And now for each number, for each number, I am checking for that for 32 bits that if my current bit is set in that number. How we check a bit is set at that particular index or not? Like if I have 010 and I want to check is my 0th bit is set in that number or not. So what we do one left shift by j, and one left shift by j means here we have j as 0. That means shift my 1 by 0. That means we have 1 here. If I do a AND with this position, you will clearly see this will get 0. Someone who don't know bit masking or how to check a bit is set, this might feel a bit hard, but let me boil down it for you. This is nothing but using this index, we are just checking if at jth index my ith bit is set or not. That means if at jth index my number have binary configuration as 1 or not. So this is a syntax for that. What we do, let's say if I have 5, the binary representation of 5 is 101. What we do 5 and 1 left shift by j. This means shifting my 1 by j bits. If I have 1, if I shift my 1 by 1 bit, so 1 would come here. If I again shift it by 1 bit, then 1 will come here. And when we do left shift, it is basically multiplying by 2. I shift my 1 by 1 bit, so now we know this 010 is the binary configuration of 2. If I again shift it by 1 bit, overall, if I again shift it by 2 bits from here, it is binary representation of 4. So is this syntax actually do the same. It takes the AND with this. So when I would be at 101, and it will say shift my 1 by j is 0, 0th bits. So we will get 1 only, 001. And if we do the binary representation, if we calculate the bitwise AND for this, we will actually get for 5, we will actually get 1 at this position and 0. That means we can, this bit is set in my this number, and we can clearly see, yes, this bit is actually set in our number. So I will just, in my bit array, at the jth position, I will increment this. Next time, I want to check my this particular bit. So I will say, is my 5 and 1 left should by j. J would be 1 here this time. J would be 1. This means now I am checking 101 with 1 left by 1. 0, 0, 1. 1 left by 1 bit, it would be 0, 1, 0. That means 2, 0, 1, 0. And if I do the bitwise wand of 101 and 0, 1, 0, it clearly is 0, 0, 0. This means our current bit is not set. And we can clearly see the current bit is not set. Similarly, we do this thing, and we at the end of the array, I would having this in this array, I would be having the number of set bits for all these. And I think if you get this line, how we are checking that if current bit is set in or not. So if current bit is set, we are just incrementing my bits of j. That means I am incrementing these count. Next time again, if this I bit is set for some number, I will make it 3. So now I have set bits for this. Now, what I ask you, the Cartesian product. Now, since I have 32-bit array and I know all the set bits at each position, I know the 1 count would be bits of 5 because I am maintaining that only. The 0 count would be n minus bit. You can also set this is set bits and this is unset bits. And the number of unique pairs would be nothing but 1 count into 0 count into 2. Why we did 2? That's I'm explaining from the very beginning because xy and yx are two different pairs. 1 count into 0 count into 2. And I'm just adding these pairs here. This condition, even though we don't write this, it will work fine. This I'm checking like if I have all 0 or all 1, that means there we don't need this operation. And you already know if we have all bits at 1, then there will be no pair form which have 1 0 or 0 1 state. So using this 1 count 0 count, we just form the Cartesian product into 2 because we x, y, and yx are different pairs, and I just calculate here. So within this syntax, I first calculate the number of bits at each position, number of set bits at each position using this vector. And then I, for at each index, I just get the number of set bits and number of unset bits, and now I know the pairs which will additionally be counted in the difference pair. So the time complexity for this code is, it would be like n cross 32 for maintaining this bit array, plus 32 for again checking this, and a space complexity of 32. Now we can actually eliminate this also. I come up with this approach so that you get to learn this, how we actually maintain a bit array to count the bits for each position, the set bits at each position. So for this, you will use this piece of code in many of the upcoming problems. So how we maintain the number of set bits at each position. But in this problem, we can actually do better. What if I am calculating these? Is there anything that I directly can get one count and zero count? Actually, yes, we can get. How? Like either of iterating for n cross 32. If I iterate for 32 cross n, what do you think? Either of iterating n cross 32 and forming this bit array. What if I do 32 cross n? If I do 32 cross n, that means this is going to run for 30 times, and I can check each bit 32 times because 32 bits, and I can check each number ith position. Does that make sense? What I am saying, even either for iterating n cross 32, what if I iterate for 32 cross n, and I can check for this n, I can check for all ith position at once. I think this would be, this makes sense for you. N cross 32 and 32 cross n. If I do 32 cross n, then using this syntax, I can actually check all at once the number of set bits, and I can just keep a count variable, let's say set count, or sorry, set bit, and if the bit is set for this index, I will uh, increase the count. Otherwise, if it is not set, I will increase the count for unset bit. And then the same thing, this operation we can do in this here only. And let me show you. I think when I do, things will be more clear. What I do in this code, we are iterating for n cross 32, and we are actually calculating for bits. For these n, like first I am going for all n, and for a particular number, I am calculating for all its 32 positions. Like if this bit is set, if this bit is set, if this bit is set, if this bit is set. For every number, I am going for all 32 bits. But here, if I go with 32n, I can, since at the end we need this index count, like all set bits of 0th position. So I can actually 32 cross n, I can, for this number, I can check if my 0th bit is set for these all numbers. So let's come to code. Let's first make a long num answer equals to 0. And let's say for I is equals to 0 till I less than 32 plus I, because in a binary number we have 32 bit at max. It can be represented in 32 bits. Now, if I iterate for my array j less than n plus j, let me make two variables, long set bit equals to 0 and unset bit equals to 0. And now I am checking for each number, I am checking if it is ith bit is set or not. So if, how we check, if ARR of j and one left by I, because I am checking for every number, I am checking its ith bit only. If it is ith bit set, I will say plus plus set bit. Otherwise, I will say else plus plus unset bit. And now, since I know the set bit and unset bit for this index, let's say if we have this These all are binary representation. At the end, I need this set bit for this line, or for this index, for this index, for this index. Now, after this iteration, I already know the set bits and the unset bits because for every number, for we go for 32, and we for 32 we cover all n ith bit. So after this loop, I know the set bit and unset bit for this index. So I can just perform the Cartesian product here only. I can say answer plus is equals to set bit into unset bit into 2 by 2. I'm explaining from the very beginning, and nothing, just this. I hope this I have not done any mistake and this should be working fine. Okay, set bit, is there any spelling wrong? Unset bit is right, unset bit. Okay, 80. Let me run for the like test cases given by them also. This is a test case which I got failed because I was not doing like from zero, but I was doing for I and j plus 1. So when I was doing I and j plus 1, the number of pairs are not, it is not taking pairs with like ji pairs are not coming. So four, okay, like let's submit this, and I think this should be work fine. I know the previous codes that I showed to you may find a bit longer. Like let me refresh it. May find a bit longer for you, but the motive behind explaining this code, because this piece of code you are going to use for many problems in future, that how you maintain a bit array that is actually keeping the count of set bits at each position for all numbers. So since we have 32, integer can be represented in 32 bits. So we for every number we I know the count of ith bit sets, and this logic is very helpful in upcoming problem. And again, I will tell you one more thing. If it is integer, if it is a big number, long, then this 32 comes to 64 because long is represented in 2 raised to up to 63. So we take 64. Binary is represented from 2 raised to the power 2 up to 2 raised to the power 31. And if it is a long number, it goes till 63. So this 32 will turn to 64 there. If it is a long. Since here it is int, we are int, so that's why this works fine. So this piece of code, and this is nothing, 32, because I know the counts for all the bits stored in bits. Zeroth count I get from here, and I just do the same thing here. After this iteration, I know the number of set bits because we grow 32 cross n. So for ith bit, I know all the ith bits, how many bits are set in the ith position for all these numbers. So I can just perform this here only. And by this, we solve this problem. The time complexity for this code is now 32 cross n, and the space complexity is order of one constant. Earlier it was 32, but why I explained this, because that calculation or like how we maintain bit array is very important when you solve upcoming problems. So like let me write the time complexity here also. It would be order of 32 cross n, 32 cross n, and space complexity is order of 1. So earlier also the time complexity is same, but we have plus 32 also because this calculation I was performing later. But here, since we have count for that index here only, so we can just do this. I think you get some learning from this video, and you get to explain, you get to understand this problem. So thank you. This is all from my side, and not at this side.